Next, let's talk about another characteristics of graphs called concavity. There will be two definitions here, concave up and concave down, and a rule to test to determine when a graph is concave up and when it's concave down. So here's a description. Take a look at the graph on the picture on the right. This is the graph of y equals x cubed. And while it's pretty easy to see that this graph is increasing over its entire domain, in other words, from left to right, the function is moving upward, we do notice that the function turns in different ways, or we might even be able to say it bends in different ways. And in the interval negative infinity to 0, the function seems to be bending downward. And on the interval 0 to infinity, the function tends to be bending upward. And what we call that bend or turn is concavity. So let's take a look at the tangents from left to right and see if we can learn a little bit more. If we pick any point on the interval from negative infinity to 0, where we say that the function is kind of bending downward, where we're going to label concave down, the tangent lines decrease in slope. And I think you can see that as we draw them in from left to right. We go from a slope of a tangent line that's fairly steep until we get closer to the end of that concave down domain where they're almost flat. So they would have a very low but still positive slope. Next, on the interval where we are concave up, we start with a tangent line that is seemingly pretty flat, but as we move further along, that tangent slope increases in value. So what does that mean for us now calculus-wise? Well, we see that from left to right that the slope of y prime either decreases or it increases. It decreases on the interval negative infinity to 0, where we are concave down. And it increases on the interval 0 to infinity, where we are concave up. And that's the slope of y prime, not just y prime. Also notice where the curve lies. Anywhere that the function is concave down, the curve lies completely below the tangents. So we've got the tangents drawn in red. Here's the curve. It's completely below all those tangent lines. And where we're concave up, the graph lies completely above all of those tangent lines. Sometimes that's used as a definitive piece to describe where a function is concave down or up. So let's get into a more formal definition. The graph of a differentiable function y equals f of x is concave up on an interval I if y prime is increasing on that interval. Then it's concave down an interval y if y prime is decreasing on that interval. And so if we take that one step further, we know how to determine whether a function itself is increasing or decreasing based on the previous video and previous lesson from mean value theorem. We know a function is increasing if its derivative is positive. So our function this time is not y but y prime. We want to show where y prime is increasing, and to do that, we would look at the derivative of y prime. What's the derivative of y prime? It's y double prime. So wherever y double prime is increasing, aka positive, or y prime is increasing, aka y double prime positive, the function is concave up. And then if y prime is decreasing, we want to look at where its derivative, which would be given by y double prime, is negative. And that's what we say here. If a function has a second derivative, we can conclude that y prime increases if y double prime is positive, and y prime decreases if y double prime is negative. So that leads us then to the test. The graph of a twice differentiable function y equals f of x is concave up on any interval where y double prime is positive, concave up when the second derivative is positive, concave down on any interval where the second derivative is negative. So that takes us to an example. Let's use that concavity test to determine the concavity of the given functions on the given intervals. So let's take a look at the function y equals x squared only on the interval from 3 to 10. So here's how that test is worked. First, we want to take the first derivative. That's 2x. Then we want to know where that first derivative is increasing or decreasing, so we differentiate again. Y double prime is 2. And on the interval from 3 to 10, that second derivative, I'm going to label this y double prime, is always 2, which means it's always positive. And if the second derivative is positive, the function is concave upward. So what I would give as an answer here is that y double prime is concave up on 3 to 10, since that second derivative is always positive. Let's take a look at part B. Y equals 3 plus the sine of x on the interval from 0 to 2 pi. So if the first derivative, the derivative of 3 is 0, and the derivative of sine of x is cosine x. The second derivative is negative sine of x. We want to know where that is negative and that is positive. So let's see if we have any critical numbers to the second derivative. So we want to set it equal to 0. We know that sine of x is 0 when x is equal to 0 or pi or 2 pi. Now 0 and 2 pi are the edges of the interval, so those don't really help us much here, but we do have a second derivative critical at pi. So we want to set up a number line then that begins at 0 and ends at 2 pi. That's our interval. We have a critical at pi, and this is a test of y double prime. So y double prime there. Now, pick a test value between 0 and pi. I'm going to pick pi over 2. In the second derivative, that's here, negative sine of pi over 2 would give me a negative 1. So that means from 0 to pi, y double prime sine is negative. Then let's pick a test value from pi to 2 pi. How about 3 pi over 2? Then the second derivative would be negative sine of 3 pi over 2. That'd be negative 1, which would be positive. And that makes me conclude from the concavity test that y double prime negative means we're concave down from 0 to pi and concave up where y double prime is positive from pi to 2 pi. So my answer here would be this function is concave down on the interval from 0 to pi, and it's concave up on the interval from pi to 2 pi. Next, we want to try exercise 7 from your textbook. It goes like this. Same directions, use the concavity test to determine the intervals on which the graph of this function is concave up and concave down. So when we think concavity, we think second derivative. So the first derivative, y prime, is going to be a 12x squared plus a 42x plus a 36. Y double prime will be now a 24x plus 42. Is there anywhere in the second derivative that this function is equal to 0? And I check that because that would be a potential place for the second derivative to change sign from positive to negative or negative to positive. I see I can factor out a 6 from this expression, leaving me with 4x plus 7 equals 0, and that means a second derivative critical would be negative 7/4. So my number line then goes from negative infinity to positive infinity, since this is a function defined on the entire real number line. I have a partition where x is negative 7/4, and I'm testing y double prime. So let's take a look at a test value between negative infinity and negative 7/4. So how about negative 2? In the second derivative, plugging a negative 2 in would give us 24 times negative 2, which is negative 48. Plus 42 would be negative 6, so y double prime is negative in this interval. Next, a test value between negative 7/4 and infinity. How about 0? 0's in that interval. 24 times 0 is 0, plus 42 would give us 42. So on this interval, y double prime is positive. My conclusion is we're negative here and positive there. So for an answer, I'm going to say this function is concave down on the interval from negative infinity to negative 7/4 and concave up on the interval from negative 7/4 to positive infinity. And that ends it for this video in this section.